Talking about my master's thesis in multi-scale analysis of composite materials using calculus and the generalized method of cells, an open source implementation. On the top left, we're showing a picture of what we are all familiar with about how matter is composed. It's composed of atoms. Then we have a next larger scale, length scale, where we have a microstructure. It could be typically your bones have a microstructure. The composite materials is composed of fibers and a matrix and an interface. And then we have different type of configurations in what we call the mesoscale, leading to a microscale like a chair, a table, a composite laminate on a car or a wing on an aircraft. So my job was to develop a connection between a finite element open source code and a NASA code that does micromechanics analysis at a microscale level using some micromechanics theories. So on the top right hand corner, I show what we call a micro or a structural finite element model. On the top left, on the left side, we do a localization of the element and we apply the micromechanics properties onto each one of the integration points of the element. So what that leads us is to a better and more efficient way of analyzing a structural behavior of large-scale structures. That is really helpful. For example, we're trying to understand how in the bottom corner we show that's a sampling of a bone structure that had some decalcification process. So you can see that because the microstructure changes over time, you can actually have different properties changing, or the effective properties at the microscale are changing. You need to change that to compensate in your structural modeling. We want to understand, for example, when you break an arm, let's say you want to do a surgery on a hip replacement or a knee replacement. We want to understand the underlying effective material properties at the microscale and combining that with a macroscale finite element model. This is really, if you try to do this only on the finite element, it would be really expensive and you would have to spend a lot of computational time to get down to the micro level. If you can see it there, you have a large box, but we're really talking about orders of magnitude small in the sense of the fibers and in your bones of the trabecular bone. So we are trying to address cost efficiency, fidelity, and accuracy in our modeling. Thank you.